We will impose gauge invariance into the Dirac-Lagrangian by changing the covariant derivative into a gauge covariant derivative. We saw that the covariant derivative was responsible for breaking local gauge invariance. So the idea is to add to the covariant derivative a term which will cancel this term in order to restore gauge invariance. And for that it has to be a function of space-time because del alpha is also a function of space-time, and it has to carry a Lorentz index because the covariant derivative carries a Lorentz index. Therefore it has to be a vector field. And the IE is just a constant added here for convenience. Any resemblance to an existing vector field and to an existing coupling constant is of course not coincidental. But for now, mu is just introduced as what we called a gauge field. In order for gauge invariance to be restored at the end, we need to specify how the gauge field transforms under gauge transformation. Of course, because mu is transformed, we need also to transform d mu, the gauge covariant derivative. We can now use this transformation to show that by changing the covariant derivative into a gauge covariant derivative restores a gauge invariance in the Dirac-Lagrangian. We need to compute the action of del slash dash on exponential I alpha psi. By moving the exponential to the left, we need to take into account the action of the covariant derivative on this exponential. So by moving the exponential to the left, changes del slash dash into del slash. So we just showed that by changing the covariant derivative into a gauge covariant derivative, restore gauge invariance into the Lagrangian. Let us now rearrange this expression for the Lagrangian in order to recognize a sum of the initial Dirac-Lagrangian plus an additional term. We recognize that in addition to the Dirac-Lagrangian, we now have a term which couples the fermionic field with the gauge vector field mu, and this is nothing else but just the QED interaction Lagrangian. So our initial goal was only to restore local gauge invariance into the Dirac-Lagrangian, which initially is supposed to describe just a free fermion. But in doing that, we introduced an interaction term between the Dirac field and the gauge vector field, which we had to introduce in order to restore the gauge invariance. This means that there is no such a thing as a free fermion, because we want to have gauge invariance. We need to have interaction, and QED arises naturally from gauge invariance requirement applied to the fermionic field.